Hello everyone. In this presentation, I'll be discussing about spaceborne LiDAR observation of elevated aerosol layer in the free troposphere over South Asia, technical challenges and recommendation. I really thanks Satyabhama Institute of Space Science and Tech Satyabhama Institute of Science and Technology, Chennai for this theme-based workshop and invitation. This is the outline of my presentation. Since the LiDAR is mostly used for atmospheric aerosols, it's very important that what are aerosols and why we need LiDAR for aerosol observation, or why we need LiDAR observation for aerosols. Then we'll briefly discuss the LiDAR basics, motivation of the study which we carried out using spaceborne LiDAR, important results, challenges, and recommendation. So let's start. The atmospheric aerosols are ensemble of particles, which solid and liquid particles suspended in the atmosphere. And it has, because it has a wide sources, the size vary from 10 to the power minus 3 micrometer to 10 to the power 2 micrometer. So in order of 5 magnitude variation in the size of aerosols present in the atmosphere. The concentration goes as high as up to 10 to the power 8 per cubic centimeter. So we have a few photographs to illustrate you what are different types of aerosols which are there in the atmosphere. So we have a sea salt from marine origin. Then we have dust, volcanic aerosols from volcanic eruptions, particles from the vehicular emission, and also from industrial emission, and also the organic matter from the biomass burning and so on it. So once these particles are emitted into the atmosphere by several mechanisms, it get transported at higher altitude and they get distributed in up to within the troposphere, let's say up to 16 to 18 kilometers. So there are variety of platform by which we can measure the vertical profile of aerosols such as aircraft, balloon borne, and satellite. The aircraft and balloon borne or snapshot measurement. We cannot have a continuous measurement. With satellite, we can have special, the large, especially we can have measurement of aerosols in a wider spatial scales, but at poor temporal resolution because satellite has overpass time 1 day, or in our case, the satellite which I am going to refer in this talk is Calypso, which has 16 days overpassage. At a given location, it repeat after 16 days. So obviously, the LiDAR serves as the best platform or best instrument to make use of this instrument for to provide high temporally resolved vertical distribution of aerosols. So what is LiDAR? So LiDAR is basically is an active remote sensing technique, which is very similar to radar. The basic principle of LiDAR is very similar to radar, but it works at slightly smaller wavelength range, mostly in optical range. So the basic principle is that it emits the laser into the atmosphere and receive the back scattered due to presence of particles molecules in the atmosphere. So this is the animation of how lidar works. So the laser of given power and wavelength is transmitted into the atmosphere, and once this laser pulse is transmitted, it travels and encounter the atmospheric aerosols, air molecules, and the fraction of radiation because of this scattering and absorption, it goes back in the direction of transmitted beam to the receiver, which is a telescope, and then it goes to PMT for further signal enhancement, and then it goes to data acquisition. So this is the how the return power of the received signal varies as a function of altitude or time. So this is the right panel showed that the schematic diagram of how lidar works. So for example, this is the normal, and from with respect to normal, if this is, or with respect to horizontal, if there is an angle of the transmitted beam, and when the transmitted beam encounter the different layers of the atmosphere, let us say layer 1 and layer 2. So the from layer 1 we get the signal that is stored with time stamp. Then further it goes, because it will not stop here. It goes further, it penetrates further, and from there also we get the return signal. So that signal is also the stored. So for each signal we we know the time. So since the speed of light is known, we can calculate the range, and that is shown over here. So we define two important variables, which I'll be referring: back scatter coefficient, which is nothing but 180-degree returns of the transmitted signal. It's basically signal strength of the return signal. Then extinction coefficient, which is basically once the light, the laser pulse is transmitted, it may absorb or scatter depending upon the nature of aerosols. And we define the extinction coefficient is the sum of the absorption and scattering of electromagnetic or a wave by the particles suspended in the atmosphere. So this is the block diagram of a LiDAR system, which showed how different hardware systems are integrated to provide a meaningful measurements. So we have a transmitter which basically transmit the laser pulse into the atmosphere, and this laser pulse interact with the object we call scatterer, and the fraction of radiation is returned back toward the receiver of the telescope or of the lidar, and then it goes to the controller and data acquisition, optics, and so on. And then it goes to the data analysis, and then derivation of several physical variables such as backscatter coefficient, extinction coefficient. So the transmitted, so we have defined different terminology here. This is the transmittance which I have expressed over here with a function of z. So on the way to the object, and from the object back to the receiver. So we have transmission terms two times, and then the lidar equation using this block diagram can be expressed as shown over here. So this is the received power. So this is basically a block diagram for a generic lidar system, but I'm writing the equation for an inelastic lidar, at which for which the lambda, the transmitted and received signal has the same wavelength. For elastic lidar, the wavelength of the transmitted and the received signal is same. There is no change in the wavelength of the electromagnetic wave. That's why it is called elastic. So this is the equation of an is an elastic lidar, which is expressed over here. So the transmitted power will be proportional to the amount will be the proportional to the power of the transmitted beam. This is the received power, this is transmitted power. Then the how efficient are optics, that is basically optical efficiency. So different terminology I am going to show you in the next slides. So as you can see from here, so we have the received power, then we have the average power of the signal within the range beam, then we have optical sensitivity, how of sensitive or optics, then the delta Z, which is range beam, 1 over Z square, the field of view of our telescope, and then overlapping function, overlapping corrections, then the backscatter coefficient, which is contributed by molecules and airs. As I mentioned that in the atmosphere, both are there, and our lidar transmitted signal and received signal will be influenced by both the species molecules as air molecules as well as the atmospheric aerosols particles. And then this is the, the transmission term t square, so it becomes 2 times of this integrand, so it is shown over here actually. So I'll come back to this equation once again to explain this, but I just wanted to define 3 important variables: the range beam, then the solid angle, and overlapping corrections. Here. So this is the lidar volume or range beam we call, which is shown over here. So the when we transmit the laser pulse, it has certain width. So there is a terminology called leading edge and trailing edge of the pulse. So leading edge signal will be received at later time than the the signal from the trailing edge, which is shown over here. This is the the pulse width. So this is the trailing edge and this is the leading edge. So this R1 or Z1 will reach in time t, but the signal from R2 will reach much faster than t minus tau, where tau is basically the effective pulse length. So the difference between these two is expressed over here. It is delta AR or delta Z in our equation, which is shown over here. So this is basically the length of the volume or scattering volume from which the back scattered light is received at any instant of time. It is called the effective or pulse length. Now the next is overlapping corrections. So what happened because of the large back scatter at near surface, there is a the backscatter radiation will not be captured by the receiving telescope. Some fraction will be, away from the receiver telescope, within out of the field of out of the field of view of the telescopes. Will not be so receiver will not be able to capture those backscatter. So at near surface you find that there is a the transmitted beam and received beam, which is a little divergent beam, will not be, coincided. So there will be mismatch here, and it is mostly at near surface. But as you go up, so this the 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 risk the backscatter signal will be, aligned, and it will be within the field of view of the receiver telescope. So you'll get the maximum radiation within the field of the telescope. So you can see here, above this altitude it is perfectly overlapped. So there is all the backscatter is basically collected by the telescope. So we have overlap, OZ, the overlapping correction is 1 inch. But in between these two, here it is completely zero because both the receiver and transmitter are off. And in between these two, it will vary between 0 to 1 inch. So this is how the overlapping correction works in the looks like in the LiDAR. The solid angle, which is very simple, is basically the field of view of the receiving telescope, which is defined by 1 over zx, where A is the receiving telescope surface area, and z is the distance from the scatterer, in this case aerosol particles. Now I'll go back to this equation, and so if you look at this equation very carefully, that, and if I transfer this equation, this z squared term, I can rewrite and take the log of this. I'm sorry, I think I have forget here. I need to write the log of this one. Okay, so then the right hand side, because a lot of constants are there, and if you integrate or differentiate with respect to z, most of the constant term will vanish here, and you will get this equation. So this is called the range corrected signal. Z square I have shown here, 1 over z square. So if you uh, multiply the z square with the received signal, you get the range corrected signal. So we need to I am replacing this equation, the representation by sz, which is range corrected signal. So you basically get the form of this equation as shown here. So if you solve this equation, you will get, on the left side you have range corrected signal, but right side you will get two variables. Okay, so you have only one equation but two variables, beta and alpha, where beta is the uh, sum of the backscatter due to air molecules and particles, and this alpha is also contributed by both aerosol particles and air molecules. So, but for air molecules, beta and alpha are known. So what we have unknown here is that beta for particle and alpha for particles. So basically two unknowns and one equation. So it's impossible to solve this equation. So we need to basically represent these two variables, beta and alpha, and define a third variable which can be then expressed uh, in by the ratio of these two. So we define the Lidar ratio, which is the ratio of uh, the extinction to the backscatter coefficient. So then you express other one variable with the other in the by multiplying the Lidar ratio with the beta aerosol. So alpha can be replaced with this, the product of Lidar ratio. So this Lidar ratio has to be known actually. So what we do here, that to get the Lidar ratio, we must have an independent aerosol optical thickness measurement, maybe from radiometer or sun photometer or multi-wavelength radiometer, and get that the aerosol optical thickness. And you as start with certain assumption, okay, because you have to iterate this equation by an arbitrary Lidar ratio. Okay, so first you start with a assumption, and then fine tune that Lidar ratio in such a way that the aerosol optical thickness derived from Lidar should match with the aerosol optical thickness derived from the measured from the sun photometer. So accordingly, you fine tune the Lidar ratio to get the best match between uh, aerosol's optical thickness derived from Lidar and the sun photometer measures aerosol optical thickness. Now with this basics, I just wanted to go to the results. So we conducted a balloon experiment over Hyderabad, and this is the profile from the balloon, two balloon borne measurements of black carbon aerosol and composite total aerosol section. So on the x-axis, on the left panel, the x-axis is mass concentration of black carbon aerosol as a function of altitude, and the right panel is the mass concentration of composite aerosol at two size bins as a function of altitude. So as you can see from these two graphs, that at 4.5 kilometer we have an elevated layer. This also indicates some presence of elevated aerosol layers. Unfortunately, pump didn't work after this altitude, so we had to stop this observation. But this also indicates that the at 4.5 kilometer we have high aerosol loadings in the troposphere. Recent balloon borne measurement during ISRO NASA battle campaign also depicted that between 4 to 6 kilometer we have elevated aerosol layer during monsoon. Please do remember that this was conducted during pre-monsoon, that is March and May, and this experiment was conducted during monsoon times. So during these two seasons, we could see elevated aerosol layers present between 4 to 6 kilometers. So this is the uh, the the aerosol number concentration profile as a function of altitude for one instrument that is called MCPC, mixing condensation particle counter. And then also we have few other optical particle counter, LIOPC and POPs, which provides the number concentration of aerosol at different channels. These are the size channels of aerosols, size, the size of the aerosol particles. So you can see here that the the observation made by MCPC uh, reasonably agreed with uh, the aerosol concentration at made at this band, the at least this region, 4 to 6 kilometer. Now very recently there were there was a there was an aircraft campaign over the west, northwest, and Indo-Gangetic Plain and northeast part of the Indian region. And this study also showed elevated aerosol layer up to 6 kilometer. More precisely, the aerosol concentration within the region, within three troposphere and boundary layer, showed very contrasting concentration. For example, the organic matter dominated within the boundary layer. You can see from here, within the boundary layer, while the sulfate particle dominate in the free troposphere in the Indo-Gangetic plain in northeast India. Whereas during northwest pre-monsoon, the sulfate was dominant species outside the Indo-Gangetic plain. But both the profile showed aerosol elevated layers between 4 to 6 kilometers. So we design a study to look at whether the elevated aerosol layers are present throughout the season and throughout the Indian subcontinent. So for this reason, we designed a research and divided entire Indian subcontinents into 6 subzones, which are shown over here: North India, South India, West, Central, Indo-Gangetic Plain, East India. And we utilize Calliope, which is a spaceborne Lidar, and the details are given over here. It's level 2 version 4.28 between 2008 to 2018, and this is the result obtained from that Calliope observations. Extinction coefficient. So on the y-axis you have altitude, and for different season, rows are for different season ranging from winter to fall, and the color bar showed the extinction profile, extinction coefficient in logarithmic scale. As you can see here, that the extinction coefficient exhibited sizable vertical gradient, being highest below 2 kilometer, within 2 kilometer in the boundary layer, and extending up to 4 kilometer during winter and spring, winter and fall, and reaches up to 6 kilometer during the spring and summer season, suggesting that the elevated aerosol layer between 4 to 6 kilometer, and we named as elevated aerosol layers. Now, it was uh, intended to look at that whether to the statistics of such layers, how significant those elevated layers over different season and over different region. So we developed an algorithm, a search algorithm, to derive 3 important variables: the Z minimum, that is the lowest altitude of the elevated aerosol layer, and Z peak is the peak, the highest value of extinction coefficient of the profile. This is Z peak, and Z maxima, it is the highest point of the elevated layer above which the extinction coefficient decreases. So this is the Z minimum, Z peak, and Z maxima. But we applied several threshold because this is a very idealistic case of aerosol profile, but the actual profile will be different than what I am showing here. For that reason, based on several iteration, we developed this search algorithm to derive the 3 layer parameter: Z minimum, Z peak, and Z max, which I defined here. And we calculated then geometrical layer thickness by taking the difference between the Z maximum and Z minimum. So this is basically the geometrical thickness, and then we integrated the extinction coefficient within this between Z minimum and Z maximum, and we get the layer aerosol optical thickness, which are depicted over here. So on the y-axis we have a probability density function, and on the x-axis I have shown all three parameters: jet peak, then geometrical layer thickness, and the layer optical thickness for uh, four different seasons shown in four different colors for 6 regions. So what we found here is that the elevated aerosol layers were found to be persistent between 4 to 6 kilometers. Between 4 to 6, you can see the frequency of occurrence, and occasionally reached above 6 kilometer, and and also showed very large spatial and temporal variation over the study region. We also noticed a very significant spatial inhomogeneity in the layer thickness. As you can see here, their spatial distributions are very different for different season, and also it varies from season region to region. What we found interestingly is that the positive skewed distribution of uh, layer aerosol optical thickness in winter and summer, but enhanced aerosol loading within the ZLT during summer compared to other seasons. Now, when we carried out the Calliope observation, looking at the layer heights at different season or at different location, prior to that, we compared with the ground truth LiDAR observations just to validate and see the performance of space-bound LiDAR with respect to ground truth observation. So we carried out this study for two different locations in India: Kanpur, which is Aeronet, which is the MPL network, and Hyderabad, which was the station for which was operating the boundary LiDAR from National Atmospheric Research Laboratory, Karanki, for 1 year period during April 2009 to March 2010, and we compared the extinction coefficient for these two locations. So Calypso derived extinction coefficient, as you can see here, agreed very well with the boundary layer LiDAR below 3 kilometer up to 35%, but it deviate, by an order by a factor of 2 above 3 kilometer. So the large difference could be associated with the weakness from the high altitude for a ground based LiDAR, because the Calliope showed high concentration even above 3 kilometer, which was missed in boundary ground truth LiDAR. So that could be a limitation of ground based LiDAR observations, which we need to look into that. Now, during this analysis, what we also found that if you look at the daytime and nighttime profile obtained from Calliope, they are very different. So nighttime and uh, nighttime aerosol extinction coefficients. This is the a typical the for just for sake of completeness, I am showing you for one zone, one region, that is South India. On the x-axis you have extinction coefficient, and y-axis is the altitude in kilometer, and for 4 seasons: winter, spring, summer, and fall, for day and night. Okay, separate, shown in black, red, and blue color. So nighttime profile, nighttime extinction coefficient profile were very smooth because of this high signal to noise ratio, and the low SNR or elevated aerosol layer in the daytime profile compared to nighttime profiles. So you can see here that the lot of the the kinks in the extinction coefficient profile, especially between 4 to 6 kilometers. And this is the reason where other ground the aircraft measurement and balloon borne measurements are also showing elevated layers. So it was impossible for us to assess the possible region, because we don't have the ground truth LiDAR observation up to 12 kilometers. Now we may, based on our analysis, we recommend that we need to improve the Kaliof algorithm for daytime profiles. And also we need to improve the capability of ground truth LiDAR observation up to 12 kilometers with an improved signal to noise ratio. And it would be very useful if we have a LiDAR network over Indian region so that we can further study LiDAR elevated aerosol layer at much higher temporal resolution using ground truth LiDAR. So with this, I thank you, and I want to thank all the collaborator for this study, and once again thanks the organizer for this workshop and inviting me for this talk. Thank you very much. If you have any question from participant, you can write to me. I have provided my email ID in my first page, so please feel free to contact me for any clarification. Thank you.